Now we come to lecture 5. Having seen the earlier cycles, Otto, diesel, dual combustion, Carnot, let us have a look at the Stirling cycle. The Stirling cycle is a thermodynamic cycle that describes the operation of a class of equipment generating or operating machines. The Stirling engine is an external combustion engine. Stirling cycle is a closed cycle, that is the working fluid, which is usually helium or hydrogen. Helium is very safe to use. The fluid causing the cycle is permanently contained in the apparatus. It is not externally discharged, or it remains in the fluid remains in the apparatus that performs the cycle and does not exchange with the outside. The Stirling cycle is reversible. It can be used by generators to obtain mechanical energy from the application of heat and a cold source. We will have a look there. Or heat and a heat pump. This cycle is used to obtain thermal heat or cold energy by applying mechanical energy. That will be the reverse of this. So let us look at this. There is a hot cylinder. There is a cool cylinder. This is a piston. This is the piston. Both these pistons are connected to the engine crankshaft. This is the crankshaft, and at the end there is the flywheel. Inside is a regenerator. What is a regenerator? Is nothing but a heat exchanger. The advantage of this engine is that it has a low level of noise and vibration, and we'll see the applications subsequently. So when this piston moves down, this goes up, and you will see, it will become clear when you see the PV diagram. Now, the ideal Stirling cycle, let us have a look at the ideal Stirling cycle. It has 4 thermodynamic phases which act on the fluid. 1 to 2, isothermal expansion. The expansion compartment is heated from the outside, and contained gas has an isothermal expansion, and the contained gas has an isothermal expansion. 2 to 3, the transfer of hot gases to constant volume, isochoric it's called. The gas then passes through the regenerator, yielding part of the heat, which will remain available for a later phase. Part of the heat is released, and the remaining some of it will be used in the subsequent cycle. 3 to 4, isothermic compression. Fluid in the combustion space is cooled by help of this cooling cylinder. 4 to 1, heat transfer at constant volume. The fluid flows back through the regenerator, recovering the heat from the same regenerator. So this completes the 1, 2, 3, 4 and back to initial stage 1. This is all done by the hot cylinder, cooling cylinder and the regenerator, which is a heat exchanger. Now let us look at the PV diagram of a real cycle. On this PV diagram, let's say the cubic centimeters of the engine of the space is, or the contraption is, this is 1100, 1200, 13, 14, 15, 1600 cc. We have got a 1600 cc contraption. The pressure is shown in bars on the pressure scale: 9, 10, 11, 12, 13, 14, 15. These are bars. One bar, as you know, is 0.1 MPa. Here you will see that the 1 to 2 starts from here. 1 to 2 isothermal expansion, heated from the outside, and then 2 to 3 at constant volume, means come here, this is constant volume, this is 2 to 3. 3 to 4, it is isothermal compression from 1500 to approximately 1100 cc. And the fourth, heat transfer at constant volume, takes place around slightly above 12 bar and stops at around 14.5 bar. From there, then again the first comes to the first initial position, and this is the actual diagram in the lab which is performed. These are the readings taken. These are the 4 angular positions of the crankshaft. 360 degrees. Crankshaft revolves twice. So one revolution 360, 90 degrees, 90 to 70. Now, what are the uses of this Stirling cycle? It is used in toys, heat power plants in businesses, stationary electric generators, and even to some extent vehicles. And the most important, because as I said, because of its low level noise and vibration, there is virtually no vibration. It is used for powering the silent submarines, deep water, deep ocean submarines. Now, this is the Stirling cycle. Now let us come to the last cycle in our syllabus, the Ericsson cycle. The Ericsson cycle is also an external combustion engine. It was invented by an American named Ericsson in the year 1840 for running a hot air engine ship, hot air in the skies. Before the IC engines were invented, the first was the hot air engine ship. It consists of 2 isothermal and 2 constant pressure, and this 2 constant pressure cycles, the other phases, replaces the 2 isentropic cycles of the Carnot cycle. We know that the Carnot cycle is almost fully efficient. It is the most efficient cycle. Thermodynamically reversible, cycle is reversible thermodynamically by the action of a regenerator. Regenerator we saw in the previous. What is the function of the regenerator? A heat exchanger. The cycle is used in manufacture of closed thermal expansion, weak heat addition. Cycle used in manufacture of closed type gas turbines. I beg your pardon. It is used in manufacturing of closed type gas turbines. The fluid remains, in this case also, enclosed in the system. It does not with the outside, does not go outside. Now let us see the 4 stages of the compression of the Ericsson cycle. This is the PV diagram. This is the TS diagram. 1 to 2, isothermal expansion, or heat addition. Heat addition, temperature 1 to 2, heat is being added. Air is heated at constant pressure, 1 to 2, constant pressure, 1 to 2, pressure is constant, from T1 to T2. The second phase is 2 to 3. 2 to 3, constant pressure or isobaric heat rejection. The air is allowed to expand isothermally, that is at constant temperature T2, T3, it expands, T2, T3 expands from 2 to 3, from initial volume V2 to V3. We know that a part of heat supply in first stage is utilized for doing work in isothermal expansion. Three to 4, isothermal compression, compresses. 3 to 4, the volume compresses from 3 to 4, and isobaric heat absorption. Finally, at constant pressure, 3 to 4, isothermal compression, it is air cooled at constant pressure from initial temperature T3 to T4. T3, T1 is equal to T2, T3 to T4. This is the 3 to 4 isothermal expansion from 3 to 4. And the last phase is 4 to 1, 4 to 1, 4 to 1. Constant pressure, isobaric heat absorption. Finally, the air is compressed isothermally at constant temperature, 4 to 1, this is temperature, constant temperature, T4 to T1, from the initial volume V3 to V4. We know that some heat is rejected by the air for doing work on the air. I'll repeat, we know that some heat is rejected by the air for doing some work on the air subsequently. Hence, heat supplied during the process 1 to 2 is equal to the heat rejected during 3 to 4. Equal to 3. Because T2 minus T1 is equal to T4 minus T2 minus T1 is equal to T3 minus T3 minus T4. T2 minus T1, T3 minus T4. T3 minus T4. The efficiency is same as that of the Carnot cycle, as I mentioned earlier. So now that we've seen both the Stirling and Ericsson cycles, let us see what is the difference between the two. Firstly, both the cycles are for external heat engines, that is external combustion engines, that utilize regeneration. Both use regeneration. The main difference is that in the nature of the regeneration process, this needs to be noted, the main difference is in the nature of the regeneration process. The regeneration process for Stirling is at constant volume, and for Ericsson is at constant pressure. Well, this finishes the various cycles. In the next lecture, we will move on to the remaining part of Unit 1. Thank you.